Hi, I'm going to talk about my poster titled Transverse-Electric Surface Plasmon in Graphene Under Uniform Strain. Summary. In this work, we investigate theoretically the light reflectance of a uniformly strained monolayer of graphene embedded between a photonic crystal and a dielectric medium when illuminated with transverse electric, TE, polarized light. The results indicate that graphene holds promising applications for the development of optical sensors based on the excitation of TE plasmons. Introduction. Graphene is a two-dimensional material composed of carbon atoms arranged in a hexagonal lattice that form sigma covalent bonds within the graphene plane and possess a free electron in the 2pz orbital, which is responsible for its optical and electrical properties. In recent years, graphene has attracted considerable attention due to the fact that its electrical, optical, and chemical properties can be modified by external parameters such as applying voltages, doping, or straining it. In the context of light-matter interaction, which is the focus of this study, the excitation of surface plasmons in graphene plays an important role in the development of sensors for biological and chemical materials. For this reason, we focus in this work on the excitation of surface plasmons. A plasmon is a quasi-particle that represents the collective oscillations of electrons in a conducting material. These are generated when the free electrons of the material respond collectively to a disturbance such as light. In graphene, surface plasmons are excited through coupling with the incident electromagnetic wave, that is, the momentum or wave number of the light matches with the plasmon. A simple method to excite surface plasmons in graphene is the Kretschmann configuration. This setup consists of a high refractive index prism beneath a conducting material, which may be metal or graphene, and an external dielectric medium, usually air. When a beam of TE polarized light is incident on the prism at an angle greater than the critical angle, total internal reflection occurs. Part of the electromagnetic field of the evanescent wave transfers its energy to the free electrons in the conducting material, and when the momentum of the evanescent light matches with the momentum of the surface plasmon, the plasmon is excited. At a specific angle, the intensity of the reflected light experiences a drop due to the absorption of light for plasmon excitation. This effect is used to detect changes in the refractive index of the external medium, and consequently for the development of sensors. Theoretical approach. In this work, the structure of our problem consists of a one-dimensional photonic crystal made of silicon dioxide, dark gray color, and titanium dioxide, blue color, coated with a uniformly strained graphene monolayer with strain along Z equal to 0, and covered by a layer of PMMA, polymethyl methacrylate. The entire system is surrounded by two semi-infinite dielectric media, silicon dioxide as the substrate and air as the semi-infinite medium on the right side. The photonic crystal introduces a periodic modulation in the refractive index of the incident light, allowing its momentum to acquire additional components due to diffraction and scattering. This facilitates coupling with the surface plasmons in graphene. Additionally, because photonic band gaps are formed within the photonic crystal, the electromagnetic field becomes enhanced near the graphene interface, which increases the likelihood of exciting surface plasmons. Moreover, the PMMA layer allows for the confinement of the electromagnetic field within the graphene monolayer and also serves as a protective layer to reduce oxidation, molecular adsorption, and humidity. This helps preserve the electrical and optical properties of graphene. To account for strain in graphene, an anisotropic tight-binding model is used to describe the behavior of electrons in the material. A small perturbation in the nearest neighbor hopping energies is considered, since strain alters the interatomic distances, which in turn modifies the hopping energy. Based on this, the effective Hamiltonian around the Dirac points is derived. With the aid of the current operator, the optical conductivity of strained graphene is obtained. This conductivity is expressed as the unstrained optical conductivity multiplied by a strain factor, which depends on the strain tensor of the hexagonal graphene lattice and the exponential decay coefficient of the nearest neighbor hopping energies. Here, epsilon represents the strain magnitude, theta the angle at which the strain is applied, and nu is the Poisson ratio. The figure shows the band structure of graphene, where the conduction band, upper band, touches the valence band, lower band, at specific points known as Dirac points. A closer view of this region reveals a linear energy dependence. However, as a strain increases gradually, the Dirac cones shift until they eventually merge, forming band gaps. At this point, the model is no longer valid, which occurs when epsilon exceeds 0.22. In the contour plot, the polygonal lines define the first Brillouin zone, and the red dots indicate the Dirac points. In this image, a uniform strain of 0.2 was applied in the zigzag direction, clearly showing the shift of the Dirac points. To obtain the analytical expression for reflectance and transmittance, the transfer matrix method was used. This method allows us to study our multilayer system by relating the system's state at one point to its state at another, using a matrix. By linking the coefficients of the incident and transmitted fields, the transfer matrix can be constructed, where P represents the propagation matrices through the different media and T the transmission matrices between two media. From the transfer matrix M and the Poynting vector, the analytical expressions for reflectance and transmittance are derived. Results and conclusions. The figures show reflectance plotted against the angle of incidence for different values of strain magnitude, strain angle, the value of Na, which corresponds to the medium adjacent to graphene on the left side, and the frequency of the incident light. As observed, the sharp drop in reflectance corresponds to the excitation of the plasmon. For phi equal to 90 degrees, increasing the strain magnitude causes a shift in the reflectance dip and a reduction in its amplitude. For epsilon equal to 0.2, similar results are found, with the difference being a greater amplitude decrease at lower values of phi. In the other figures, it can be seen that the reflectance dip is sensitive to the refractive index of the medium adjacent to the strained graphene and to the frequency of the incident light, with the highest excitation frequency reaching 240 terahertz. The reflectance dip corresponds to partial absorption of energy from the TE polarized incident light, which indicates that a higher amplitude corresponds to better light-matter coupling. This occurs when the applied strain is perpendicular to the propagation angle of the surface plasmon. In these figures, the magnetic field of the photonic structure was also plotted. The magnitude of the electric field starts at nearly zero in the substrate and reaches a maximum at the interface between the photonic crystal and the PMMA layer, that is, where the strained graphene is located. It is also worth noting that for epsilon equal to 0.2 and phi equal to 90 degrees, the maximum field amplitude is achieved. In conclusion, it has been demonstrated that the reflectance dip associated with the excitation of a TE surface plasmon in strained graphene depends on both the magnitude and direction of the strain. The best absorption in graphene is obtained for epsilon equal to 0.2 and phi equal to 90 degrees. Therefore, this photonic structure is a promising candidate for detecting small changes in the environment surrounding the strained graphene and could potentially be applied as a plasmonic sensor or optoelectronic device. Thanks for watching the video. See you later.